And so welcome to Big Data for today, our official start. And we're getting really close to the end of the semester, so we only have really one last topic to cover, and that's this web search final project. Again, this project is not due this coming weekend, but you have until the end of next weekend to complete it. And I do recommend, though, that you not put it off too long, because there's a big computational part to the project that could take maybe 3 or 4 days, or possibly more, just to actually run the stuff once it's all working. Plus, there's always weird things that come up about actually getting it working. So recommend getting started on that as soon as you can. Last time in class, we did an overview of kind of the first part of the project and getting it up and running, and we kind of stopped at the point where you actually have to start writing code, and didn't really talk about that part very much. And so today we're going to continue talking about that. So I'll share my screen now. And before actually talking about the project and the material for the class, I just want to give you all another reminder that there is the required reading/viewing in this class, and the due date for this will be the end of finals week, so the same time when your final exam is going to be due. So there's no need to do it right away, but keep this in mind as something that you'll have to do before class is over. And so when you get a chance to, you'll want to do this. And again, my hope is that this will be hopefully a rather light thing, so not something stressful, but easy and hopefully enjoyable. Okay. So our search engine project, remember or recall that it's divided up into a number of tasks. These first 2 tasks, 0 and 1, are just about getting the actual project up and running so that you can start working on stuff. And that's mostly related to Git and Docker issues. Then this task 2 here is divided up into 2 parts. This task 2A is the downloader of a particular work file. So this WARC is pronounced work, and these work files are records of a web crawl. And so the Internet Archive and the Common Crawl that have these big petabytes of data that are archiving information on the internet, they store all that data in work archives. And this task 2A is going to get that and add it into your search engine so you can search that data. In a little bit, we'll talk about the details of the work file, because we'll need to know that for task 2B. But for the 2A task, there's not actually any Python coding involved in it or any SQL coding involved in it. It's just getting this download work service up and running, be able to do it, and have several of these processes running in parallel. The task 2B is where the sort of the meat of the assignment is going to be, the most difficult parts. And this is going to be the part that actually involves programming. And so this is today we're going to talk about the material that you need for the programming part of this task. Before getting into that, though, I'll just highlight that there used to be one last task, task 3, that involved actually speeding up the queries, writing some indexes to making these web searches go fast, and doing some other SQL programming. I've decided, though, to take that away. That I know we all are tired at the end of the semester, have lots of other things going on with thesis and other finals, other projects and classes. So I think without this, you can still get the main ideas of the project, and so I've done this part for you, and you won't have to. Okay, so we'll talk about, again, task 2B today. And in order to actually talk about this, we're going to step back from this file and from this code and go over to the lecture notes for week 13, and we'll spend a fair amount of time talking about some of the theory behind these work files and how they work, how you work with them. And then once we finish that, we'll come back to how that applies specifically to this assignment. I guess before doing that, are there any questions about anything related to the assignment? Okay. So in this tab right here, I have opened the week 13 notes, and we've covered a lot of these notes so far, and I scrolled down to the part where we left off about the work files. And again, this is where all the crawl data for the Common Crawl and the Internet Archive are stored in this file format. And this file format just stands for Web Archive, so that's what WARC stands for. This is the standard format for storing web crawl history. It was invented by the Internet Archive. If you, the Internet Archive actually has a really good history of their entire project on their webpage. And you can see that this file format has evolved over time. That we'll talk about today, some of the mistakes in the original file formats, that they weren't actually storing all the information that you need to really capture the important things about a web crawl. So as one example of a previous file format, there was the ARC file format. But WARC has really become the standard for web crawls. It's the thing that the Library of Congress, for example, uses when they archive like Senate web pages and government web pages. And basically everybody now has agreed that the WARC captures exactly the amount of information that we need to do a good web crawl. And so, yeah, what it does is it provides a complete history of the HTTP session. So HTTP is the protocol that is used on web pages. So on your URL in your web browser, you always have at the very beginning either HTTP:/ or HTTPS://. Those are both the same thing, except the S stands for secure. And so in order to talk about this work file and exactly what is inside of it and how we'll use it, we'll first talk about these HTTP protocols, these sessions, how they work. And this link right here goes to this web page for mozilla.org that has a really good overview of the whole thing. For our purposes, though, this is the only graph that we really need to focus on. And this graph shows a high-level overview all of the technologies involved in getting the information from whatever web page you're looking at into your web browser and viewing it. So at the top here, we have various programming languages, HTML, CSS, JavaScript. These are responsible for actually the code that displays the web page. And then this HTTP protocol is one of the network protocols involved in transferring this information over to you from the server. HTTP doesn't exist on its own. There are a bunch of these other protocols as well. And let's see, a networks course would talk in detail about the difference between all of these protocols and what they do. And it turns out that you actually don't even need any of these protocols to work with HTTP or web pages. There are other ones as well that you could work with, but these are the common ones that 99% of people use in practice. For our purposes, the only one that we'll actually care about is the IP down here. And this is going to get stored in these work files because some web pages will respond differently depending on your IP address. These other protocols, they're cool and important, but not for web scraping purposes. So let's come back here. And the key thing that we need to observe is that it's not enough just to store the downloaded content when you're doing a web crawl. So it's not enough just to store the HTML and the CSS and the JavaScript that you get back, because that actually doesn't tell you the information you need to understand what to do with the web page when you're analyzing it. And there's two, I think, really clear examples about why this is the case, but these are just like, there's like 1% of the actual things that arise. So the first example is status codes in HTTP. So HTTP has this big list of status codes that the server gives you whenever you view a web page. The most common one that you get is this 200 OK status code. Every time things work correctly, this is the status code that you get. But you've also probably seen the like 404 error codes before. So if I just type in a bunch of gibberish up here, then we get this error page saying the page doesn't exist. And this is a valid HTML page with valid CSS that we got back here, but it's giving us a 404 error code because the page doesn't exist. Every web page handles these 404 error codes differently. So Wikipedia doesn't even actually say that there's a 404 error code. GitHub has a kind of cool example of like a nice Star Wars theme 404 error code right here. But yeah, the key unifying thing is that these web pages don't exist. And so we don't want to put them inside of a search engine. And if we were to accidentally put them inside of a search engine, then what we'd see is that there's just like thousands of, oh, that's actually a page, thousands of, or millions of web pages that would have this exact same text that you just keep adding one letter to this. Oh dear, what did I do? Keep adding one letter to things up here and it will give you the same text. And so as you're crawling the web, you would, if you're adding all of these things to your search engine, you're just really bloating your search engine and you don't need to be storing all this information. So in your in the work archive itself, it stores all of the status codes that it receives from web pages. But in your program, in your search engine, you're only going to want to extract the URLs that correspond to a status code of 200, because that is the status code for a successful web page, that the web page actually exists. The other, and again, that information is not stored in the HTML, not stored in the JavaScript, not stored in CSS. So there's the only way to know that is if you store some of this network protocol, and that's inside of these work archives. The other thing that's really important about the work archives is we need to know the encoding of the web page. So recall that the encoding is how we know how to convert the raw binary bits that the network transfers back and forth that's stored in the files. How do we translate that into letters that actually get displayed? And the sort of default encoding these days is UTF-8, but not all websites use UTF-8. So I'm going to click right here. Oops, this is the one we want. And this is so some statistics from the Common Crawl archive about different encodings that they have on their in their data set. And so you can see UTF-8 is the most common, like almost 93% of web pages use UTF-8. But if you just assumed UTF-8 for everything, that's 7% of web pages that you will not be able to access. And those are going to specifically be, or especially be the non-English web pages that you won't be able to access. So this encoding right here is an Ascii encoding. It's just for English languages. So this and this are effectively the same thing for English text. This encoding right here is for Russian text. This one here is actually the official encoding of the People's Republic of China. And so all Chinese web pages that are somehow government related to China use this encoding rather than UTF-8. And we talked about this a little bit before, that UTF-8 is relatively inefficient for Asian languages, that it uses 3 bytes per letter rather than 1 or 2 bytes per letter. And China didn't like that. And so they wanted to make their, understandably, make their systems use less bandwidth, be more efficient. And so they have their own encoding to do that. And it's possible to set the encoding at the HTML level. So some websites will have one of these two lines inside of them that specify what the encoding is, but that's not required to do. And actually most websites don't do that. Instead, most websites store this information in the HTTP message that gets sent over the network to your web browser when you access a web page. And so we actually have to store that information, store the information in the HTTP request in order to see what that encoding is. And let's see, here it is. So here is what an actual HTTP header looks like, the request that comes back to you when you contact a web page. And it has, so like the particular timestamp that this happened on. The most important one though is this content type charset equals with the encoding right down here. And so again, this is not stored in the HTML, not stored in any of the files themselves. It only exists at the protocol level. And so this will be stored in the work archive, but not in the files themselves. Let's see, any high-level questions about the, actually one more link about the work archive. Here is the common crawl. When we were looking at this web page before, we saw that each of their data sets, each of their crawls has three formats: the work, the WAT, and the WET. The work is the one that we'll be using. And here they show the actual format of the work archive. At the very top up here, it has the information from the all the levels below the HTTP level that is important. So in this link right here, it has all the information from this blue section that is important to crawling web pages. And then it has the entire HTTP header right here. And again, this part's going to be important because it stores the encoding information. And then down here is the actual HTML content or JavaScript or CSS or whatever it is that was being downloaded from the web page. In order to access all of this information, we'll be using a Python library that parses through these work files for us. So you won't need to understand the file format in detail, but instead you'll just need to understand what kind of information is actually getting stored in here. So I'll switch over to the code now for a bit. And here, what I have opened up above is this downloader-host.py file. So this contains this is the file that you'll have to modify for this task 2B. And there's these three fix-me's right here that you'll have to implement. And each of these, the tasks of these fix-me's is to somehow extract information from this work archive so that we can stick it into the database. One of the, again, the general principles when we're working with any sort of big data analysis is that we want to, so this is going to be a relatively computationally intensive task that we're scanning here terabytes to petabytes of data, depending on how much you download. And we wanted this to happen not on the database itself, because that's the bottleneck of our entire system, but we wanted it to happen on separate containers that can run totally independently and statelessly. And so this downloader-host.py is in its own service, the downloader host service, that will get run and again run in its own container. The library that we'll be using in order to do this task is called the Cdx Toolkit right here. And there's a link to the documentation in the notes. And so that's the what you'll need to reference in order to actually implement this right here. These two parts right here, if you actually have a work record, so a work record corresponds to one of these segments inside of the giant work file. They're basically just appended one after the other in the work file. Once you have one of these records extracted, then you'll there's a set of functions, member functions inside the record class that allows you to access all of these pieces of information that you'll need to insert into the database. As a good reference to make this a little bit easier for you, there is the downloader work.py file, which is again something that I've fully implemented for you. You don't have to implement yourself. And it has the rough idea of how to do this. You have to make some minor adjustments, but you can at least see that, okay, we have this record. Here is the member functions that we can use to access the actual particular URL that we're, in this case, getting. One of the things that's different between these two files is that, so again, in the downloader host, we are looking for, say, every work record that comes from the New York Times spread out over thousands of different work files, potentially millions of different work files. So downloader host is one host name, one domain name, but many work files. Downloader work is one work file, but many, many host names or domain names. And because of that, the structure of the code is a little bit different. In the downloader work file, this archive iterator right here comes from that Cdx library, and it just returns a generator of records, and so you very easily get access to the records this way. In the downloader host, there is this iter function inside of Cdx, which iterates over a URL which represents a search path to what's called a Cdx Query Engine. And this Cdx Query Engine gives back a set of results, and you'll have to extract, use the documentation to figure out how to extract the records from the results. So let's see, the next thing that I want to look at is how this Cdx Query Engine looks. Maybe before I do that though, are there any questions so far?
This may be a bad question, but why don't they just use something like JSON for work files?
That's a great question, actually. So yeah, if we come over here, we can see that the file format is not in JSON. It's yeah, it's in this special work format. And the question is, why didn't they just use JSON? And there's two answers. The first answer is that JSON didn't exist when work files were first being created. So the Common Crawl was in, or sorry, the Internet Archive was started in 1996. I forget the year that JavaScript was actually created, but the J in JSON comes from JavaScript, and it wasn't even the very first version of JavaScript that had this JSON support. It was a much later version of JavaScript. So, so in that sense, it just would have been impossible to do. In a even though if JSON did exist, it's not something that they would have wanted to choose for this particular use case, because JSON is a relatively verbose format, really designed for human consumption rather than machine consumption. And when you're storing, so the Common Crawl has dozens of petabytes of data. If you had an additional 5% overhead because of JSON usage instead of this custom format, well, 5% of 50 petabytes is a lot of data that's just sort of wasted storage. That's a couple hundred extra hard drives that they have to purchase, which they wouldn't want to do. So JSON is great for smaller things, but when you get into the petabyte range, people try to make their own formats that really shave off every unneeded byte. That's a great question. Any other questions so far? Okay. So we're going to talk about this Cdx server and how it works. So here I'm on this Common Crawl data page with all of their sort of smaller data sets, and we'll just pick one basically at random. They all have this same sort of format. And here is what I'm looking for. At the very bottom, there is this link. It says Columnar Index. So columnar, like column. And if we click that, oops. There we go. This is the one to the left is the one that I wanted. The one to the right talks about the implementation, and here takes us to the actual index itself. And here you can search for any URL. So we could do something like newyorktimes.com and then with a star at the end. This star is like the glob in Bash. It will match anything. And so this matches any URL that that is hosted on newyorktimes.com. And if we pressed search like this, then it would give us what's called an index file. And let's download this real quick. And you can see that, let's go ahead and make this a little bit bigger. So each line is relatively short. The URL key right here contains the actual URL that has been downloaded, but notice that it's in this sort of reversed format. The hostname part right here is in this reversed format. So instead of saying newyorktimes.com, it's comma New York Times. They also strip off these sort of unnecessary prefixes like www. And then the other important part, so this has the actual URL that has been scraped. The other important part is this file name right here, which contains the actual work archive that needs to be downloaded in order to get this URL here. And then there is an offset right here, which shows you exactly what portion of the file name of this file do you need to download. So in order to get this particular URL right here, you don't need to download this entire file. You can only need to download it starting at this particular location. And then it has this length, download this many bytes starting at this location. So it's, yeah, if you do that, much more efficient than downloading the entire file. See, I'm gonna press Shift G. Right now I'm inside Vim, so I'll press Shift G to go to the bottom. And so you can see that there are about 15,000 lines here. So 15,000 different New York Times URLs contained in this one, crawl right here, this 1 month. There's about 100 or so different months. So that's about 1.5 million or so URLs from New York Times are included in the Common Crawl. Let's see, coming back over to the code. So right here. And we'll first, again, look at the downloader work. Inside this for loop, it's looping over the archive iterator, so looping over a single work file. Here, it is looping over this iterator, which accepts a URL right here. This URL is something that's going to be formatted and created for you automatically, but it is the URL to that search engine that we were just looking at, and it gathers up all of just the locations in the work files that it needs to download, and then returns those as the result. So you won't need to manually do that search. You won't need to manually figure out which things you have to download. This library will do it for you automatically. But you will have to look at this library to figure out what exactly to do with this result value, because it's a little bit different than how you do it with this archive iterator. Are there any questions about any of that?
Not that we're going to use it, but what does the actual, like, the starting value looked like almost a memory address? When it says start reading at a certain value, what does that mean? Is that like a character index?
So you're talking about, like, what exactly is this offset?
Yes, sorry, I forgot that it was called offset.
Yeah. So this is the number of bytes into that file that it should start the download at. So when you actually download from a like you click a link on a web page, one of the things that your web browser sends to the server is what is the initial byte of the file that you want and how many bytes do you want to download. And basically for every web page that you visit, it's going to be start at the beginning, start at byte 0, download the entire thing. But this is useful in particular when you say downloading a big file, the download gets interrupted and you try to re-download it. Firefox or Chrome is able to restart your download midway because HTTP has this feature built in. And so it's using that same feature here in order to only download part of this file right here. Good question. Any other questions so far? Okay. So yeah, this search index here is they're not actually using Postgres to implement this search feature. They're using a different database, but the underlying technology is the same. They have basically a B tree or a gin index that's supporting this search, and you're going to be querying that remotely in order to add the data into your web page. And that's everything that we'll need to know about the work files and how to access them. But the next is, like, how do we actually, once we have, say, an HTML page, how do we extract useful information out of the HTML itself? And let's go back over to the notes over here. I'll quit out of this. And that's this section right here. How do we actually extract information out of HTML? And so for our search engine, there's going to be 4 pieces of information in particular that we'll want to extract. So the text of the web page, so that we can search on keywords, the description and the title, both are the things that get displayed on the page of results. And these 3 things are the main 3 things that, I guess, standard search engines like Google, Bing, Baidu all look for. This third one, or this fourth one right here, though, is something that is unique to our search engine, the publication date. And that graph at the top displaying which or how many matching articles were published on any given day requires that we be able to extract the date of publication from the web page. And so we'll talk about how to do that right now. The basic idea, or a very key vocabulary word that you'll hear people talk about a lot, is the semantic web. And the idea of the semantic web is that, well, by default, and back in the day, HTML web pages was built really just for human consumption and not built for machine consumption. And so there was no big structure, overall formatting to the web page. People just sort of did whatever they wanted. And as all of these companies come along that wanted to automatically process these HTML web pages, they added sort of recommendations of how people can structure their web pages so that we can extract information from it. Turns out that there are now lots of these standards for how to structure web pages. So here I've listed 5 of the most common. Basically, all the major companies, so like Google, Facebook, Twitter, have their own sort of standard that they recommend people use in order for for your web pages to work well with their systems. This Dublin core and this JSON LD system are more academic inspired ones of various academic researchers wanted to be able to do things not supported with the commercial ones, and so they've generated their own. I want to take a real quick look at what these look like inside of HTML. And so here, this web page is just, so it's actually a fairly recently published web page, but it contains just a standard HTML boilerplate that some web dev includes in all of their web pages. And one of the things that's inside of here is all of these meta tags right here. These meta tags contain this semantic web sort of information. And so you can see there's this description tag right here, page description. There's this OG colon title, OG colon description. Anything that starts with OG colon, that OG stands for Open Graph, and that's Facebook's particular protocol. Twitter is obviously Twitter's protocol. Anything that doesn't have sort of a abbreviation in front of it, that is what's effectively Google's standard protocol. It was originally developed by the W3C, the World Wide Web Consortium, but in many ways, well, let's see, and this consortium back in the day before Google was kind of a body that had many different academic and commercial interests on it. They're working together to define what a good semantic web should be. It still exists. It's still mostly collaborative, but because of Google's dominant market share now, Google can basically say, I don't care what you guys say, we're going to support this a certain way, and everybody has to follow along. So, oops, here we go. Yeah, so there's a bunch of different standards for encoding this information in web pages. But there's two problems with this. The first one is that it turns out that most web pages, if they're trying to implement one of these standards, actually implement them wrong. And a very, very common way that that happens is with publication dates and how they get formatted. So basically, everybody in the world thinks that we should write dates as year, month, day, going from biggest to smallest. But for whatever historical reason, Americans think that the day should come before the month, and very often write things year, day, month. And all of the standards say that everything must be year, month, day, but a number of American websites insist on doing year, day, month. And so you have to, when you're extracting this information, have special cases for those web pages if you want to actually get the correct dates out. And then a handful of other websites choose to, for whatever reason, not follow any of these standards up here, but implement their own standard. So BBC is the biggest one that I know of that's, I don't know why they choose not to implement any of these standards if they're making some principled stand against Facebook and Twitter or something. Certainly they can afford web devs to know about those systems, but they choose not to. They implement their own thing, and so you have to have custom code that handles BBC. Fox News is a weird one because there are thousands of Fox News websites on the internet. There's the main sort of Fox News, but then every city in the US has their Fox News San Diego and Fox News LA, and all of those are handled totally differently. Some of them implement Twitter standards, some of them implement Facebook standards, some of them implement no standard. So it's all very confusing. And so the takeaway is that you won't have to deal with any of these standards directly. You won't have to parse the this information out directly. And instead, you can use this library down here that I have that tries to do all of this for you automatically. And if you click that link, it'll take you over to this repository right here. The library is called Meta HTML because it extracts meta information out of the HTML. And it extracts quite a bit of different types of meta information. But again, for our purposes, the one that we're really going to care about is this publication time right here. And let's see, here is an example output of the library. Let's see. Yeah, this timestamp published right here, again, is the thing that we most care about. And the way this is formatted is this whole thing is a JSON blob, and then the timestamps are formatted with a high and a low component. So different websites provide different granularities about how accurate their publication time, how accurate it is. So some only provide the publication year, some provide year month day, and then what is this? CNN.com provides accuracy up to the second. And so in order to encode how accurate our timestamp information is, the way it does it is it provides a range that we know it is somewhere between these two values right here. So this one has up to second level accuracy, but depending on what these range values are, it might be different for different systems. In order to use this library, the easiest way to use it will be again to reference that downloader work file. So I'm going to come over here, move over to the downloader work, and down here extracting the meta information from the library. It's extracting here, so meta HTML.parse just actually returns this JSON value from the HTML. And so it first does that, and then it calls the pspacey library to actually do the lemmatization on whatever language was found in the from the meta HTML. And then it's going to, let's see, you store all that in these variables. It'll store all of that into this dictionary right here with the JSON-B value, and then these pspacey title and content are the TS vector representations. And eventually that's going to get passed into this bulk insert function, which actually efficiently does the inserting 100 or 1,000 at a time, depending on what the setting is. In the downloader host, you'll have to extract all that same information right here. But the actual, once you have the information correctly placed into these variables, the rest of the code is all the same. It's going to put it in the dictionary and then do the bulk insert. And again, that's all implemented for you, so you won't have to write this Python SQL code. That's done for you. Are there any questions about any of that? Okay, so let's come back to our notes. And I want to, let's see, actually, yeah, we'll talk about our, what the submission for this assignment is going to look like next. And there are 3 queries right here that you'll have to run in order to sort of measure the quality of the things that you've downloaded. And when I grade this assignment, I'm going to look at these 3 queries, and based on the output of these queries, I'll be able to tell whether you're downloading the work completed successfully and whether you're downloading the hosts completed successfully or not. in your actual submission, what you'll do is, so yeah, you fork this repo and then you'll edit this README file so that these, these 3 queries down here in the submission section, you'll actually put the results of running these queries on your system inside of the README file. So when grading, I'll just look at the README file and won't actually be running queries on your system itself. This one right here shows just the total number of web pages downloaded. This one right here, let's go over here and actually run it. So I just have loaded up the pSQL connection right here. And it shows every hour how many different queries you've had run per hour. So over here is the timestamps. So I just had one system running for over a period of 2 hours. Hosts is the total number of different hosts that got downloaded. So I can tell that this was using the downloader work system instead of the downloader host system because it downloaded a bunch of host files from many, many different hosts. And that only happens when you're processing an entire work file. Host path is the total number of URLs, irrespective of whether they came from the same host or not. So for host, a URL like NewYorkTimes.com and NewYorkTimes.com/articles, these would be counted as just one inside of host, but they would be counted as 2 different things inside of host path. This right here is the path of the URL. Host path query, what that does is if you have a question mark at the end of the URL and then have something like, so variable equals value and key equals value 2, this part of the URL is called the query. And so the host path query counts this as distinct from this. Yeah, let's see, you won't need to think in too much detail about the difference between all of these, but that's what they mean. The way these are computed is if you go into the schema.sql file, at the very top of the file, there is a bunch of SQL helper functions. And we haven't talked really at all about writing functions inside of SQL, but this is sort of the format that you use to write a function that you can then use later. And there are functions for a host path, for example, which actually given a URL, extracts a canonical host path from it. So given a URL like this, extracts these different host paths. See, it makes this and this look exactly the same, so it won't count those as different. But then it'll ignore things like question marks, makes those the same. Ignores capitalization, makes those the same. So it deduplicates web pages that way. That's also important in the actual counter that happens in at the top of the search engine. If it's counting the number of web pages that we want that contain a particular term, we want to deduplicate URLs that just refer to the same web page. Again, this is something that you won't have to modify, that this would have been part of the 3rd task, but I've simplified the assignment and taken that out. Any questions about this query right here, what it's doing? Okay, this query right here, so the very last one, oops, and there's a typo, there needs to be a 2 at the end, shows, so here's all of our different host names, and in this reversed format and how many different URLs have been downloaded from them. So there's another way that I can tell that that host program, downloader host, has not been run yet, because all of these have a very small number of, all of these hosts have a very small number of URLs associated with them. And this is what I would expect from the downloader work program, to have many, many different host names, each with a very, very small number of URLs corresponding to the host name. The next step is that you'll do a search through Firefox, take a screenshot, upload that screenshot here. Oops, I did not mean to click on that. There's a nice 404 page, and push everything to GitHub and submit your GitHub repo into Sakai. Any questions about that? Okay. Then one last thing on this notes page to talk about is some open research problems. So there's two that we'll talk about. The first one is crawling dynamic web pages. And so some obvious sort of problems related to dynamic web pages are if the web page has a login, so it's like Facebook or your email. Those obviously can't be crawled by the Common Crawl or the Internet Archive. You could write your own custom crawler that could do that, but that's very, very rare. Other things, so like Google search results won't get archived because of the robots.txt. We'll just disallow people crawling that. And so it'll be impossible for us, for example, to know what kind of articles would people get when somebody was searching for coronavirus in January 2020. So there's I don't know, kind of a lot of debate about like who was handling the coronavirus the better, the Republicans or the Democrats. And one of the things that has sort of really influenced that is how Google was providing search results during the time when coronavirus was, people were first discovering it and knowing about it. But that information is forever lost to history because Google's search results are dynamic. They don't store those. And yeah, so we can never know whether Google influenced the conversation in a positive or a negative way because of that. Similarly, Amazon, we can't really know their historical prices because they change their prices every day, and they even, in some cases, change their prices based on your IP address, where you're coming from. So these are things that relatively, I mean, they're obvious problems, you have to think about it, but things that most people understand. A less obvious problem, though, is this one I'm particularly interested in, is the Korean Central News Agency, the KCNA. So this is the main newspaper of the DPRK, and here's their website right here, the .kp. This is called the TLD of a domain name. The .kp TLD is the country code TLD for the DPRK. And if we were to click on this, we could read all of the latest news coming out of Pyongyang. But it uses a dynamic web page, custom code that they've made in Korea. And because of this, Google can't index this web page at all. So if we click on this link right here, and so this site:/kcna.kp instructs Google to restrict its search to this website right here. And if we search for United States, we can see that there are no search results that Google's able to return to us. But I happen to know that the KCNA talks about the United States quite a lot. It's one of their favorite things to talk about, how all the bad things the United States is doing. And so that information is essentially invisible to people who use Google. This is a purely technical issue, and it's not like related to sanctions or any sort of ideological logical things because there are other North Korean websites that Google is able to index. So the Pyongyang Times, for example, gets indexed by Google because just implementation details of how it works, but KCNA is not. So this is something that, let's see, I guess issues like this, Google has no incentive to fix because there are no advertisers who want their ads in the US appearing next to search results from KCNA. But this does provide some sort of structural censorship in the internet. We talked a little bit before about how websites like the New York Times will delete articles that for whatever reason become controversial and against the editorial positions that they're trying to present to the world. And so that's one form of censorship that web scraping is able to combat. But this sort of structural censorship is where the web scraper is not even able to access the web page, is something that that we don't really have good techniques for working with at this point. And besides KCNA, a lot of more developing countries that are less connected to the internet have this same sort of problem, that their web developers didn't grow up using Google, not experts in how Google works, how all of this search engine works behind the hood, and so they haven't developed their web pages in a way that makes searching them easy. And so for us in the United States, we don't get access to that information. For KCNA in particular, I think that's bad because we're not even able to understand what the DPRK has to say about us. We only get our information from US sources, and yeah. So I think that's led to a negative impacts on our conversation about that topic. And so I would like to develop better searching techniques, sort of equivalent common crawl for these maybe less popular web pages, or more technically challenging to crawl web pages. Other sort of research direction I'm working on in this area is that as that meta HTML library, given an HTML web page, how do we extract the article text from the web page? This is something that so it's very, very widely studied because Google essentially has to be able to do this in order to implement their own web search. They don't want to, for example, have your web search find ads on the web page. They want it to find the actual important information in the web page. And there's a lot of good research on this, particularly in English, but in non-English languages, the research is pretty much non-existent. Few European languages have this, Chinese has this, a little bit of research, but it's all pales in comparison to English and then other languages like, say, Thai or Vietnamese or yeah, more indigenous languages. There's no research on this at all. Yeah, any questions about any of these topics? Okay. Then we have one last set of notes about what are called roll-up tables and probabilistic data structures. And these are things that are implemented internally inside of this search engine in the SQL. And so it's one of those, again, parts of the search engine project that I'm not going to ask you to implement directly, but I've provided the code for you. And actually these queries down here are the queries that are related to these concepts that we'll cover today and on Monday next week. The Yeah, so the understanding of what we'll talk about today and Monday related to this set of notes will help you understand what's going on in these queries, help you understand why exactly the search is going fast, but won't be strictly necessary to actually implement the homework. At this point, we've covered absolutely everything that you need in order to do the homework assignments. So in this set of notes, we'll look at 3 problems and how to fix them. And I guess first, by the way, I don't think I mentioned this, but this is in the week 14 set of notes. So we'll start that a little bit early today. The first problem here is that count star and actually aggregate functions in general are much slower than you might intuitively think that they should be. And this is a real problem impacting companies like Instagram. So here is a tech talk given by Instagram. If you wanted to watch the video, here's a link down here. This woman here is one of their principal engineers. She didn't start at Instagram when they first were founded, but came one of their earlier employees after a year or two, and has been working with them since then. And she was the sort of the person in charge of implementing likes on Instagram. And so here's an Instagram page. And if you can see up here in the top right, it's a little bit blurry, but here is, it says 1.2 million likes. And the way that they were at Instagram originally implementing this section of the web page is with a query that looked something like this. Select count star from user likes media where this condition is here. And this is going to just count your, yeah, it's going to count, it's going to generate that number right there. The basic idea of, or let's see, internally, they have a table that looks something like this. So here's their user likes media table, and it has an id users corresponding to who has done the like, id media corresponding to what is the post that is being liked, and then they have an index on the id media, and then so this query right here is able to do an index only scan on this right here. The problem, though, is that when you have 1.2 million likes, the index only scan has to touch 1.2 million tuples in the index. It doesn't have to visit the heap table at all, but it still has to touch 1.2 million index entries, and that's a lot of index entries, and so it's relatively slow, meaning hundreds of milliseconds. So for maybe most purposes, that's well within reasonable, but if you're Instagram, a real-time web page, you don't want your page loads to be hundreds of milliseconds, and so it was unreasonable for them, and one of her tasks was to bring this from hundreds of milliseconds down to under a millisecond. And the basic idea of how you do this is that you don't want to recompute this value every time. You want to cache it. You want to, cache your results. And in Postgres, this is implemented with something called Materialized Views, which is what we'll talk about on Monday. Let's see, so when Instagram first launched in 2010, Materialized Views did not yet exist in Postgres. They were first introduced in Postgres version 9.3 in 2013. And one of the reasons they introduced them is because Instagram and other companies were running into this problem. So when Instagram was first created, they didn't have materialized views yet, and so they had to turn to an alternative solution called Memcache, first released in 2003, so it existed when Instagram was first being launched. But the disadvantage of using one of these external solutions, something like Memcache, is that it really complicates your system architecture. That now you have let's say one of the main parts of this talk is she's explaining how Postgres and Memcache, they set it up to work together, and it's a fairly complicated system. So Instagram still uses that system because they have it up and working. But nowadays, because we have this materialized views, there is no need to rely on external things like that. You can do it entirely in Postgres. Let's see. I think this is probably a good stopping point for us for today. We're a little bit early, but then on Monday, we'll talk about exactly how these, like what these materialized views are doing, how they solve this problem, and then two other problems related to materialized views and making things faster. Yeah, so that'll be our official end of class for today, but I'll stick around for any questions about anything from the material today or the homework assignment. And otherwise, I will see you either on Friday or next week.